Okay, this is problem 3 from this semester's exam 2. So in this problem you have this RC circuit, which we saw in lab, but it's asking you to find, it says at some time the voltage across this capacitor is 1 volt and the voltage across this capacitor is 0.5 volts, and it wants to know at what rate is this voltage across this capacitor changing. So to do that, we need to know that this equation here for a capacitor. So for C1, the charge on it at some time is just Q equals the capacitance times some voltage. But the rate at which that voltage is changing, then dV dt is what we want to know, is equal to dQ dt divided by the capacitance. So that's just this equation, except for we're taking the rate of change of these quantities and rearranging. So we want to find this, and in order to do that, we need to know how fast the charge on it is changing, and then we can divide that by the capacitance to get the rate of change of voltage. So the dQ dt is just how fast charge is coming onto that capacitor, which is just the current going into this branch of the circuit. So we want to know the current going onto C1 divided by the capacitance C1, and that'll be our answer. So in order to do that, we need to look at this circuit. So we have some current going in this direction. Of that, it splits here. So some current will go through this resistor, some current will build up on this capacitor here, and then some will go through this branch of the circuit. And we don't really care what happens over here. We just know that it'll all come back here. So we have this total current here, which all goes through this R1, and then it breaks into 3 sections. So this one, the one on the capacitor, which is what we want to find, and then this stuff over here. So we need to find what all these currents are in order to know how much is going onto this capacitor. So if we look at the problem, it tells us what the voltage is across this capacitor and this one. So if we know, say the voltage, let's call this voltage here 0 volts, then this voltage here is 0.5 volts, and this one here is 1 volt, and so that's just given in the problem. So we actually know the voltage here is 1 volt, the voltage here is 4.4 volts from the battery, so we know the voltage dropped across this R1, so we can find the current through there. We know the voltage dropped across R3, so we can find the current through there. And we know the voltage dropped across R2, so we can find the current that goes into this side of the circuit too. And what's left will be the part that's going onto our capacitor, and that's what we want to know. So let's find what all those voltages are, or what all these currents are. So through R1, this is the total current in the circuit. V across R1 is equal to I through R1 times R1. So that current, the total current in the circuit is VR1 divided by R1. VR1 is the voltage dropped across that, so that's 4.4 volts minus 1 volt here over R1. So that's 3.4 volts divided by 100 ohms is 0.34 amps. Sorry, 0.034 amps, or 34 milliamps. So that's the total current in the circuit, and some amount of that will come this way or through this one. So now we need to find how much splits through this resistor R3. So we want to know the current through R3, which will be the voltage across R3 divided by R3. The voltage across R3 is 1 volt. It was the same as the voltage across C1 since those are in parallel. So 1 volt divided by R3 is 200 ohms. 1 volt over 200 ohms is 5 milliamps. And then we can do the same thing for R2. So whatever goes through R2 goes through this side of the circuit. So IR2 is the voltage dropped across R2 divided by R2, which is 0.5 volts. So 1 volt here minus 0.5 volts here is 0.5 volts dropped across R2 divided by 100 ohms. And that's also 5 milliamps. So we have 34 milliamps going into the circuit, 5 split off this way, so we have 29 left going through this. I'm sorry, so we have 34 volts total going through the circuit, 5 go through R3, so 29 are left that go through here. Of that, we found that 5 go this way through R2, so a total of 24 milliamps are left to go onto our capacitor. So the capacitor is charging, with this current of 24 milliamps, and we found earlier that that divided by the capacitance is our dV/dt that we're looking for. So 24 milliamps divided by that capacitance is 1 microfarad, and this is dV dt. So if you do that, you get 2.4 times 10 to the 4 volts per second, and then that's the right answer. Okay, so part B says a long time after the switch is closed, when the charges in the capacitors are no longer charging, how do the voltages across C1 and C2 compare? So if we look back at this, we have C1 and then we have a resistor here and then C2. So let's just draw this again over here for clarity. The part of the circuit that we care about, there's this C1, and then through it, or across it, we have some other resistor, and then that splits, and we have another resistor, and C2. So this was C1, and this was C2, and then the rest of the circuit's out that way, and we don't care about it. So there's some voltage dropped here. So there's a voltage difference across C1, VC1, and then there's some of that is dropped here across this resistor was R2. And so the voltage dropped across C2 is something less than C1. So there are a couple of ways to think about this, but this whole voltage across C1 is dropped across this whole part of the circuit, and some of that will be across this resistor here. So the voltage on C2 has to be less than the voltage on C1. So VC2 is less than, VC1 is greater than VC2. Okay, so now part C, it says consider the situation where the switch is open, the ion channel represented by R3 has 0 resistance, and C1 has discharged to 0 charge. What is the RC time constant for the discharge of C2? So if you picture, this is just a wire now, and charge that's built up on one plate of this capacitor is going to go through the circuit and then back to the other plate. And the resistance that it sees as it does that is the effective resistance of for this RC time constant. This is the effective part that we're going to look for. So you can see I guess you can imagine it this way. If you were a charge that were here and you're going to try and get back to the other plate, what resistance would you see? And so you could either go across this path here and through R4. That's one possible path to get back. But you could also take this path here where you went through 100 ohms and then through this straight part of the wire here. So there are two paths you could take. So what you see when you're going back are two possible paths, one through a 100 ohm resistor or another through a 200 ohm resistor. So between plate 1 and plate 2, this is what you see, these two resistances in parallel, or these two possible paths in parallel. And so the effective resistance that you see is the parallel resistances of these two things. So in parallel, 100 ohms and 200 ohms are parallel resistance of 67 ohms. And so this effective R is equal to 67 ohms, and the capacitance was 1 microfarad. So 67 ohms times 1 microfarad is 6.7 times 10 to the minus 5 seconds, and that's the time constant.